If a massive industrial circuit breaker fails to interrupt a fault, the result is a sudden, violent arc flash. Connecting unverified hardware is catastrophic. An AC distribution board reaches the status of a safe grid asset only after exhaustive, mathematically verifiable testing proves its operational readiness. To prove that safety, commissioning engineers evaluate the equipment against manufacturer manuals, project specifications, and global standards like the IEC or IEEE. But these documents frequently conflict. This diagram outlines the reference governance rule. When standards clash, engineers must apply the most stringent approved requirement. If 3 specifications disagree, the process isolates and locks in the tightest numerical tolerance as the absolute baseline. Safety in high-voltage environments does not tolerate the lowest common denominator. Rigorous application of the strictest standard is the only barrier between stable operation and total failure. Before connecting a single test lead, engineers must establish a secure physical boundary. This requires verified safe isolation, installing physical safety barricades, and wearing appropriate personal protective equipment. The area must undergo a strict lockout and tagout process. Engineers physically lock the energy sources and actively verify the complete absence of voltage. The testing process relies on a specific inventory of tools: primary and secondary current injection kits, multimeters, megers for insulation resistance, and phase sequence meters. Every instrument must hold an active calibration certificate. The readings they produce form the legal basis of the commissioning audit, requiring unbroken traceability back to standardized benchmarks. A secure physical perimeter and precise, validated tools form the non-negotiable foundation for every subsequent step in the testing sequence. The testing sequence begins with a mechanical inspection of the breakers. Engineers verify equipment labels, check torque marks on terminals, and inspect arc chutes, and prove pole-to-pole continuity to confirm the physical hardware is intact. To test miniature circuit breakers, a secondary injection setup connects directly to the terminals to record the exact millisecond each pole trips. For larger MCCBs, primary current injection pushes up to 300% of rated current through the main contacts to force an operation. This graph maps the exact trip time and current response of the breaker against standard tripping characteristics like B, C, D, K, or Z curves. The recorded data point must fall within the specific shaded tolerance band of its assigned curve. A breaker's physical form is irrelevant until its tripping curve is empirically proven to interrupt fault currents within precise milliseconds. The commissioning sequence now shifts focus to the ACDB's control logic and alarm matrices. First, safely isolate the target relay from the rest of the board. This prevents the test from sending unintended trip commands across the live grid. Using a secondary injection kit, engineers supply direct current into the relay coil. They gradually increase voltage to find the exact pickup threshold and operating time, then gradually decrease it to identify the precise drop-off threshold and reset time. This animation shows the formula for calculating the reset ratio. Engineers divide the drop-off voltage by the pickup voltage and multiply by 100 to determine the operational health of the relay. Verifying these exact timings and reset ratios guarantees that the board's nervous system responds accurately to control signals, with no logical errors. Zooming out, we evaluate the board's primary busbars, the massive conductive elements that carry the full operational load. Before applying high test voltages, the busbars must be isolated from all potential backfeeds, capacitors, and outgoing electrical loads. Engineers use an insulation resistance tester to apply a standard DC voltage, measuring resistance phase to ground and phase to phase across the busbars. This introduces a lethal capacitance hazard, requiring the engineer to physically ground and completely discharge every tested busbar immediately afterward. Finally, they execute point-to-point phase continuity checks, tracing the correct phasing reference from the incomer section all the way through to the outgoing terminals. Proven, mathematically verified busbar insulation is the absolute prerequisite before live grid voltage can enter the system. The highest level of complexity in the ACDB is the automatic transfer switch, which dictates how the board handles 2 separate power sources. Before enabling any automatic transfer logic, engineers must verify the phase sequence across an open bus section to ensure both sources have matching rotation. Testing begins with incomer breakers closed and bus tie breaker Q2 open. The engineer simulates the loss of incomer 1. The system must recognize the failure, trip breaker Q1, and close Q2 to restore power, strictly observing the approved transfer delay. When incomer 1 is restored, Q1 recloses and Q2 opens, preventing accidental parallel. Simulating a fault on Q1, the logic forces Q2 to remain open, ensuring a healthy source does not blindly feed an existing electrical fault. By exhaustively verifying the electrical and mechanical interlocks, engineers prevent catastrophic, unsynchronized parallel grid connections. Effective commissioning requires the engineer to actively hunt for data deviations rather than simply recording results. If a breaker exhibits a delayed trip or a nuisance trip outside of the strict tolerances of a specific curve, it fails. There is no middle ground. Control logic deviations face the same zero-tolerance policy. If a relay chatters or its contacts stick, recalibration is not an option. The physical relay must be discarded and replaced. Engineers analyze insulation resistance data for downward trends. A drop in resistance indicates a root cause like moisture ingress, compromised insulation barriers, or forgotten temporary test links. An engineer proves their value by recognizing these critical deviations and exercising their authority to halt the process immediately. Before the system can be released, operations and commissioning witnesses must clear a final hold point. They confirm absolutely no unintended source paralleling occurred during testing and verify that no protection schemes remain blocked. The team now completes the physical restoration. They remove temporary test leads, reinstall physical barriers, and reset the software alarm logs. Finally, the documentation is secured. Engineers clear the punch list, compile calibration certificates, and execute the formal sign-off. The end result is a fully validated and secure system, empirically proven by data, and ready for live integration. Commissioning is complete only when the physical state of the hardware perfectly mirrors the audited documentation. That exact alignment is the only guarantee of a secure transition to the live grid.